Hey, welcome. Have you ever really stopped to think about a single ray of sunshine? I mean, really think about its journey. Today, we're going to do just that. We're going to follow a sunbeam from its wild birth inside a star all the way across 93 million miles of space right to the spot where you are now. So let's get this cosmic road trip started. We totally take it for granted, right? The sun's up, it's warm, it's bright. But the path that light has to take to get to us? It's like an insane obstacle course. Honestly, the story is way more dramatic than you'd probably guess. And it all kicks off out there, a cool 93 million miles from here. This is no simple A to B trip. It's an epic saga that involves nuclear fusion, a brutal fight with our own atmosphere, and some surprisingly simple geometry that, believe it or not, shapes our entire world. Okay, first stop, obviously, is the sun itself. This is the powerhouse, the origin point. This is where it all begins for every single bit of light and warmth we feel here on Earth. So deep, deep inside the sun's core, the pressure is just unimaginable. It's so intense that it's literally crushing hydrogen atoms together to make helium. That process? That's nuclear fusion, and it unleashes this unbelievable blast of energy in the form of photons, which are just particles of light. And just like that, our sunbeam is born. But get this, its journey is just getting started. It could take that one little photon up to 100,000 years just to fight its way out of the sun's super dense interior. Crazy, right? So, once our sunbeam finally escapes the sun's gravity, it blasts out into the huge, empty vacuum of space. And out here, its journey is actually super consistent. It's almost predictable. And to put a number on this predictable journey, scientists came up with something called the solar constant. The best way to think of it is like this. It's the raw, totally unfiltered fire hose of solar energy that's just blasting the very edge of our atmosphere, before anything has a chance to mess with it. And yep, there's a number for it. It's about 1361 watts for every single square meter. To put that in perspective, imagine a small space heater turned up to high. Now picture that amount of energy hitting a 1 meter square at the very edge of space every single second. It is incredibly reliable out there. And this right here, this is the big turning point in our story. Out in space, that flow of energy is like a perfectly smooth superhighway. But the second it gets to our planet, that highway turns into a chaotic, messy obstacle course. So, what in the world happens when our sunbeam finally arrives? So, after an 8-minute sprint across 93 million miles, our sunbeam is here. It's at Earth. But believe me, its journey is not over. Not by a long shot. First, it has to survive our atmosphere. You can think of our atmosphere like a bouncer at a really exclusive club. As our sunbeam tries to get in, it gets pushed around. Blue light gets scattered everywhere by air molecules. That's literally why the sky looks blue. Big, puffy white clouds act like mirrors, reflecting a huge chunk of it right back out into space. And then you've got gases like ozone and water vapor that just absorb some of it. Yeah, this quote just says it all, doesn't it? Our atmosphere is this life-saving shield. It protects us from all the really nasty radiation, but it's also a filter that seriously cuts down the amount of energy that actually makes it to where we live. Okay, so let's say a sunbeam has made it through the atmosphere. Phew. But there's one more gigantic factor that decides how warm it actually feels to us. The angle that it hits the ground at. And this is all about solar geometry. Just think about it like this. When the sun is way up, directly overhead at noon, its rays are like a super focused spotlight. They're concentrating all that energy into a tiny area, which feels really intense and hot. But when the sun is low in the sky, like at sunrise or sunset, that exact same amount of energy gets smeared out over a much, much bigger area. So it feels weaker and cooler. And right there, that is the whole secret behind our seasons. It has nothing to do with being closer to the sun. It's just about that simple geometry. The hemisphere that gets those direct, concentrated rays, well, that's summer. And the hemisphere getting those weak, slanted rays, that's winter. It's really that simple. This chart just quantifies it perfectly. I mean, look at the difference in energy intensity. A sunbeam that hits straight on at a 90-degree angle delivers 100% of its power. But just slant it down to a 30-degree angle, and the power gets cut in half. The angle changes everything. All right, So after this absolutely epic journey, surviving nuclear fusion, crossing deep space, battling through the atmosphere, and arriving at a specific angle, how do we actually, count the sunbeams that finally make it? Well, that's where measurement comes in. Scientists use two main tools for this. First, there's a pyranometer. It's kind of like a fisheye lens. Its little dome captures all the incoming sunlight from the whole sky, the direct beam, and all that scattered light too. Then you have the pyrheliometer, which is more like a sniper scope. It tracks the sun with perfect precision to measure only the power coming from that direct, focused beam.
So why do we care so much? Why go to all this trouble? Well, it turns out that knowing exactly how much solar energy is hitting the ground is absolutely critical for understanding our climate, for making accurate weather forecasts, and, of course, for figuring out how to build and place solar panels to get the most clean energy possible.
So there you have it, the incredible 93 million mile journey of a single sunbeam. We followed it from its birth all the way to its final destination here on Earth. We've learned how to measure its power with incredible precision, which really just leaves us with one last big question. Now that we understand this amazing resource so well, how are we going to choose to use it for our future?